Alrighty. So here's our definition for improper integrals. It states if a function f is continuous on the interval a to infinity, where it starts at a, so a is included, then the integral from a to infinity of f of x dx is called an improper integral and is defined as using a limit. We replace infinity with b, and we say the limit as b approaches infinity of the integral a to b of f of x dx. Similarly, if a function f is continuous on an interval from negative infinity to b, then that integral then the integral from negative infinity to b f of x dx is also called an improper integral and is defined as using a limit, the limit as a approaches negative infinity of from a to b of f of x dx. If the limit that you compute does not exist, then we say that the improper integral diverges. If the limit exists, right, you get a finite single real number. Let's say that this number is L, then the improper integral converges to L. Okay? So let's take a look at a few examples just to get familiar with this. Okay? Let's say my first example, example 1, we have the integral of 7 to infinity of 9 over x dx. Alrighty. In this first example, there's two things that we can do. First, you can always pull out the constant multiple. So you can pull the 9 outside of the integral. Another thing that you could do is notice that since your upper limit of integration contains the infinity symbol, or the infinity symbol, then you can rewrite this entire improper integral using a limit. So two things are happening. We're going to say 9 times the limit as b approaches infinity of the integral from 7 to b of 1 over x dx. Now, when you look at this integral 1 over x dx, you should be able to now find the antiderivative. What is the antiderivative of 1 over x? Yeah, you're going to have to apply the ln rule, so you get ln of x. So we say that this is all equal to 9 times the limit as b approaches infinity of ln of x from x equals 7 to x equals b. All right, so we're going to get 9 times the limit as b approaches infinity of ln of b minus ln of 7. All right, so ln of 7 most likely is going to be an irrational number, right? You will need a calculator to compute ln of 7. So let's focus on what happens when I replace b with infinity, right? Applying like sort of like a direct sub here. Okay, if I apply a direct sub, then what is ln of infinity? Say it again. Yeah. Not 0. Nope. It's going to be infinity, right? The ln curve is just slowly, as soon as you pass x equals 1, the graph will slowly rise up. Okay, it slowly increases without bound. So it eventually will go to infinity, right? So what we have is now 9 times infinity minus ln of 7. But if you work out this computation, right, if you take ln of 7, subtract it away from infinity, and then multiply 9, what do you think your results is going to be? Infinity. Now, because we get infinity here, is infinity a real number? No, infinity is not a real number. So what do we know about this improper integral? It diverges? Very good. So here I'm just going to write in parentheses, diverges. Good. Let's look at a second example. All right. I want to do at least three examples and give you a nice little fact, okay? Let's say that my example 2 now, we have another improper integral. Let's say it goes from, I don't know. This might not look too nice. It might look a little nasty, but it's okay. Let's say if we have 64 to infinity of 9, not 9, sorry, I already used 9. Let's say 7 over the cube root of x dx. Okay. In this example now, there's three things that we can do in the first step. The first thing that you can do is you can always pull out the constant multiple outside of the integral. That constant multiple being 7. We could also notice that the integral contains an infinity symbol, so you could rewrite it using a limit. So we're going to have 7 times the limit as b approaches infinity of 64 to b of 1 over the cube root of x. But you can rewrite the cube root of x using a fractional exponent, right? Cube root of x is x raised to what power? Not 3. 1/3, right? This is the cube root. So your 3 is your n essentially, your root. So it's x to the 1/3. Okay. Now, x to the 1/3, you can bring this up into the numerator. If you bring that up into the numerator, you're going to get 7 times the limit as b approaches infinity of 64b of x to the negative 1/3 dx. Now, this is something that we can integrate, right? You just apply the power rule for integration. If you apply the power rule for integration, you add 1 to the exponent and then divide by that sum. So what is negative 1/3 plus 1? Yep. No, well, careful. Remember, it's negative 1/3 plus 1. So 2/3, right? It's like, for example, if you have an entire pizza pie and you ate, let's say 1/3 of it, then you got 2/3 remaining. All right, so we have x to the 2/3 divided by 2/3. And this is now going to go from x equals 64 to x equals b. All right, let's clean this up a little bit. What we can do is take the 2/3 here in the denominator, and instead of dividing by that fraction, we can multiply by the reciprocal. The reciprocal of 2/3 is 3/2. That 3/2 can be multiplied by 7. So if you take 7 times 3/2, that's like saying 7 times 3 divided by 2. 7 times 3 is 21 divided by 2. And you can leave it alone. You can leave that fraction alone. So we'll get 21 over 2 on the outside times the limit as b approaches infinity of x to the 2/3 from x equals 64 to b. So by the fundamental theorem of calculus, you're going to get b to the 2/3 minus 64 to the 2/3. All right. Let's just figure out what's the 64 to the 2/3 part, and then I'll evaluate this limit. So if you want to compute 64 to the 2/3, it's easier to, I want to say, taking the cube root of 64 and then squaring that result. Right? You could take the cube root of 64 first, and then raise it to the second power. So what is the cube root of 64? 4. 4 squared is 16. So that piece is going to be 16. All right, so we have 21 over 2 times the limit as b approaches infinity of b to the 2/3 minus 16. All right, what happens when I replace b with infinity? What do you think we're going to get? We're going to get back infinity. So if you have 21 over 2 times infinity minus 16, what is my result going to be? infinity. And if we're going to get infinity as an answer, then what do I know about the improper integral? Diverges. And that's it. All right, let's look at a third example. But then I can show you a little pattern. So I'll make the third example relatively a quick one. So that way I can get to the point. In my third example, let's say we have the integral from 1 to infinity of 1 over x cubed dx. Well, this is an improper integral. You apply your definition. If I apply my definition, we have the limit as b approaches infinity of 1 to b of x to the negative third dx, right? So I can rewrite the 1 over x to the third as x to the negative 3 because I'm getting ready to compute this integral. So when I use my power rule, x to the negative 1, x to the negative 3, if you add 1 to the exponent and divide by that sum, what do you get? That's right. You're going to get x to the negative 2 over negative 2 from x equals 1 to x equals b. All right, this, to evaluate this integral, what I will do is first clean it up, okay? What I can do is pull out the negative 1/2, right? Because we're dividing by negative 2, which is like saying you're multiplying by negative 1/2. I can pull that out. If I pull that out, we'll still have this limit that comes after it. And the x to the negative 2, I can rewrite that using a positive exponent. So I can rewrite that as 1 over x squared and evaluate this now from x equals 1 to x equals b. Okay, well, if we apply that fundamental theorem of calculus here, we're going to get 1 over b squared minus 1 over 1. Now we know what's 1 minus 1, right? 1 over 1, that's just negative 1. Okay, so this piece here, that's just negative 1. Now, if I look at this piece, when I plug in infinity for 1 over b squared, we're going to get 1 over infinity squared. 1 over infinity squared is 0. So look inside your bracket. If you have 0 minus 1, 0 minus 1 is what? Negative 1. So now this is going to equal to negative 1/2 times negative 1. And negative 1/2 times negative 1 is, say it again, 1/2. Now, what do you think? Does the limit diverge or converges? Right? 1/2 is a real number, so it converges. Okay, good. You can say that it converges to 1/2, but I'm just gonna write converges for short. So there's a pattern here that I wanted to show you, and that's with the more basic improper integrals. When you're gonna get into series, because you're about to hit that soon, you're gonna learn about the p-series test. And some integrals of the p-series test looks like the following form, right? So I'm just gonna write a note. Sometimes you're going to deal with integrals that just simply looks like a to infinity of dx over x to the p. Namely, this a would usually start at 1, so I'm just going to change it. And we say the following. If you have this type of integral, depending on your power, p, it would either converge or diverge. It converges if p is greater than 1, and it diverges if p is between and including 1. So we usually say 0 is less than p, less than or equal to 1. Okay. And we saw that with the first 3 examples, right? In example 1, when I dealt with 1 over x, x was technically raised to the first power. So by this fact here, this note, we know that it would automatically diverge because p was 1. And example number 2, what was my p here? My p would have been 1/3, right? This was my p here. And since p is this value is between 0 and 1, it would automatically diverge as well. For example number 3, we had p was 3. So therefore it converges. Now, because it converges, you just can't say the final answer is convergence. You got to say it converges to something, namely a real number. You got to find that real number. Okay. Let me show you another example that I thought was interesting. I just looked at it in this book where I'll tell you the answer. It's going to diverge, but I'll show you why. Here's my fourth example. Example 4. Let's say if I have pi over 2 to infinity of sine of x dx. Okay. So you can deal with improper integrals where your function could be a trig function or an exponential or logarithmic function, but you just got to make sure that the function is continuous on that interval. Sine of x is always continuous for any real number. Okay, right? Because if you plug in any value of x, the sine values is always between what two numbers? Say again? Not 0 and 1. You're close. -1 and 1. Yep. It's always going to be between -1 and 1, depending on the angle that you plug in. All right. So we know that sine of x is continuous. So you could apply this definition of improper integrals. You get the limit as b approaches infinity of the integral pi over 2 of b of sine of x dx. Now, it's been a while that we've done this, but what is the antiderivative of sine of x? Say it again? Yes, negative cosine. You got it. So it's negative cosine of x from pi over 2 to b. Now, the negative, you could have pulled it out of the integral. Sorry, not of the integral, but you can pull it out of the limit. It doesn't really affect us here at the moment. So we're going to get negative times, or just negative, limit b as b approaches infinity of cosine of b minus cosine of pi over 2. Now, anybody remember what's cosine of pi over 2? Cosine of pi over 2 is 0. So that's going to go away. Now, what we're going to be left with is the following, right? When I directly substitute infinity, we're going to get negative on the outside of cosine of infinity. What is cosine of infinity? Huh? Not infinity. Not 1. Not 0. Think about the cosine curve. What do you know about the cosine curve? Basic features. It doesn't go from 0 to 1. It goes from -1 to 1. And what else do we know about cosine? Think about its basic features, namely its graph. What do you know about the cosine graph? You can start anywhere you want. Say it louder. No. No. The thing about cosine curve is that it's cyclic. It just keeps repeating itself, right? So, for example, if I drew out a cosine curve here on our, if I drew out a cosine curve, let's say this is 0, this is pi over 2, pi, 3 pi over 2, and 2 pi. Now, cosine of 0 is 1. So it starts with a maximum. At pi over 2 is 0. At pi, you're at -1 at minimum. At 3 pi over 2, you're at the x-axis, and then at 2 pi, you're back at 1 again. Right, so the cosine curve, the way that it behaves is that in the interval of every 2 pi, it just repeats itself. So as x is going to infinity, as x is approaching infinity, the cosine curve is bounded between -1 and 1. Right, so this piece, cosine of infinity here, we can say is bounded or oscillates. Probably spell oscillates wrong there. Oscillates is like saying alternating as well. Oscillates. Let me just look at the textbook for the right spelling. It oscillates between -1 and 1. So this limit that I try to compute here actually doesn't exist, right? So this piece here is D and E. And because the limit doesn't exist, what do we say? Diverges, right? So the improper integral that we were dealing with, pi over 2 to infinity of sine of x dx diverges. And again, that's because that limit didn't exist. All right, that was a good example. I think I'm missing one example. The one example that I haven't done yet is the lower limit of integration, where, like, for example, it's at -infinity. So I want to do one of that now. Let's say, for example, 5. We have the integral -infinity of from 0 of e to the x dx. Okay, this will be the limit now as a approaches -infinity. Excuse me, from a to 0 of e to the x dx. What is the antiderivative of e to the x? That's right, you're gonna get e to the x. Excuse me. So you're gonna get e to the, oh sorry, I need my limit statement. You're gonna get the limit as a approaches -infinity of e to the x from a to 0. So this is e to the a minus e to the 0. All right, what is e to the 0? 1. Now, e to the a will now be e to the -infinity. So we're going to get, e to the -infinity minus 1. But e to the -infinity, you can rewrite this as 1 over e to the infinity minus 1. That's right. That's going to be 0. So, sorry, I did this wrong. I swapped it by accident. My bad. Let me just fix it. It's supposed to be 0 to a. So then it's supposed to be 1 minus e to the infinity. 1 minus 1 over e to the infinity. Yep. So it's 1 minus e to the -infinity, which is 1 minus 1 over e to the infinity. But 1 over e to the infinity is 0. So your answer is going to be 1. And because we get a real number, the limit exists, we say that it converges. All right, so these are some basic examples of improper integrals. I'm just going to pause this video and make another recording. I'm going to do some more complicated examples.